it's Mr. Bennett here, and in today's video I'm going to be looking at resonance of waves, and we'll be looking at several examples of where that actually applies. So I just want to quickly show you a video that shows a very famous bridge failure.
One over the USA's Tacoma Narrows. From the day it was finished in 1940, it bounced around. Dubbed Galloping Gertie, it became a tourist attraction. Real trouble started the day it began to twist. The wind wasn't particularly strong, but it stayed steady. Each time it twisted, it turned a little more. Finally, it twisted itself apart and became every bridge builder's nightmare. For Gimsing, the answer could be seen in the wind tunnel. The problem with the Tacoma Narrows Bridge was its sharp, square road deck. As the wind hit it, miniature whirlwinds formed at the corners, which started the twisting. The twist turned the deck towards the wind, which produced more twist, and finally, disaster. The answer? Get rid of the square corners.
If you add these airfoils, the wind will move smoothly around the bridge section, just like you'll experience on the wing of an aircraft. In the case of the Great Belt Bridge, we tested a number of different shapes to find out which would give the most stable bridge, and it turned out it would remain stable to a wind speed which is more than twice of what have ever been measured in the Great Belt area.
So interesting video in terms of looking at resonance and how that actually destroyed the Narrows Bridge. Certainly it's a factor that bridge construction needs to consider, and certainly even a building construction needs to consider. So most objects have a natural frequency, so you need to make sure you dampen that frequency. So in buildings they'll have a big pendulum or a big centre wave. That they do that, and again, as you saw in the video, with a bridge they'll design it so it acts a bit more like a wing rather than just a flat space where the breeze can actually hit it, and therefore reducing the chance of having any resonance occurring. Alright, so resonance is certainly something as an engineer you would need to consider when you're building any particular structure. Alright, in today's video we're going to be looking at sound waves, and obviously we're looking at resonance. So that is essentially a standing wave that we're going to be producing. So we could look at certainly the good and the bad of resonance, and certainly the Narrows Bridge is a bad example, but there are some really good examples of where we use resonance. So we'll be looking at some of those. That relates to open and closed pipes, and obviously strings, any type of string instrument. We'll be looking at the harmonics associated with that and what the fundamentals are. Right, so, and then we'll be looking at how beats occur. Right, so should be quite interesting. In resonance, okay, here's an example, something I'd like you to do. It's one of your little demos that you'll do in class. So if we have a tuning fork, right, of the same frequency, and we tap that there, the sound wave, compression wave, is going to cause this other tuning fork to start to vibrate, right? Because they have the same frequencies, the same relative frequency. So once I stop this one over here, then you'll be able to hear the one on the right actually still vibrating at the frequency that it actually resonates at. Right? Now, that's a really important concept in terms of the good part of resonance. If you have a radio station or a TV, you get your TV, you have to tune it into a particular frequency. So what you're doing there is you're turning your TV into that particular frequency. And so when the antenna oscillates, right, so when the signal's sent out, the electrons go up and down at a certain frequency. That's what you're doing here with your antenna. You're tuning it to the same frequency so they can resonate at the same time, and so therefore you actually hear the radio signal coming in or the TV signal coming in. So that's a really useful part of resonance. Right, here's a cool example of using resonance to actually break a glass. Pretty awesome and cool videos there. Obviously, the resonance broke the glass because it had the same frequency as the glass, and so therefore once that resonated enough, it actually broke, and the levitation occurred inside a standing wave. So now to produce a standing wave, what you need to do, and we're just going to use an example of someone swinging a rope, and it's fixed at one end over here. So if you swing that rope and you rotate it, or you oscillate that rope, you're going to set up a standing wave, and a little bit like the one down the bottom there. We classify that point there as a node, and we classify the top part there as an anti-node. Alright, so what's going to happen is the rope will reflect off the wall, and if you have the right frequency, you're going to see a standing wave. And certainly I'd like you to make sure you do that in class, just to show that to yourself. Alright, so I'm going to use an example of a standing wave in a string instrument. Alright, so if you think about a guitar basically has a length from there to there of the strings. Alright, so if we think of a guitar, if we just pluck it, then we'll set up one harmonic, the first harmonic, which is a fundamental harmonic of a guitar. Alright, and we know that a full wave has this symbol here, right, like the second harmonic, so that's only going to be half a wavelength. So the frequency, right, our fundamental frequency is going to be equal to basically half the wavelength there. Alright, we know this L value here. Right, we're going to know this L value there. So we know that's a half a wavelength, and we know that therefore our fundamental will be twice that particular length here between the two frets. Now, if we go to this particular fret, which is the 12th fret, it's quite an amazing thing. If we stop there, then what we do, if we pluck our particular guitar, we'll set up a standing wave for the second harmonic. Alright, and if we also think about going the next stage, our fourth harmonic would be at the same place as well. And so at that particular point, if we're holding the strings there, we can set up a number of different harmonics at the particular stage there. Right? So that's simply how a musical instrument like a guitar would use standing waves. The other examples we're going to look at are closed and open tubes or containers. Right, so these are like obviously flutes and trumpets and all that sort of stuff. So if we've got both ends open, then our first harmonic will be simply equal to twice that length of the tube there. Right, and our second harmonic will be equal to the length of the tube, right? And our third harmonic will be equal to 1.5 times the length of that tube. So therefore, if we're thinking about that, our fundamental frequency, right, our second harmonic is going to be twice the first harmonic, and the third harmonic is going to be three times the first harmonic. Right, we're going to have a series of these antinodes and nodes, and the antinodes are where you're going to actually hear the sound. Right, so standing wave in the tube is another example of a useful application of a standing wave. We go to a closed tube scenario. Right, so that's basically a quarter of a wavelength. At that point there, it's our first fundamental. Right, our second fundamental is going to be basically 3/4 of a wavelength. Right, so and then our fifth Our fifth harmonic is going to be one full wavelength and a quarter, isn't it? Right, so if we start going through that same process again, our fundamental frequency F1, our third harmonic is going to be 3 times F1, our fifth harmonic is going to be 5 times F1. Right, so we're going to do some activities that actually look at doing this, so you can actually see whether this holds true in real life. So the formulas that we just talked about for an open pipe and a closed pipe relate to these ones here. Alright, so I would suggest that you copy these into your notes. Let's just do an example of the sort of thing that you will have to do in one of your practice. And this will allow you to work out the speed of light, or speed of sound. So when we come through here, our first harmonic is a quarter of a wavelength. So the tuning fork's held above the column. The smallest value which a peak occurs is the sound intensity at 14 centimetres. In other words, this length here is 14 centimetres. Right, and assuming the speed of sound is in fact 343 metres per second. So obviously it's a open pipe at one end and closed at the other end. So this is the formula we need to use. Right, so we're looking for the first one. So we put our velocity in. The length of the tube is going to be 14 centimetres, so that's going to be 0.14 of a metre. And so therefore the frequency works out to be 612.5 Hertz. The next part we have to do is find the length for the next two resonant frequencies. Well, that's going to be the third harmonic and the fifth harmonic. So if we put n equals 3 in there and keep everything else the same, that will work out to be 42 centimetres. And if we put the fifth harmonic in there, that's going to be 70 centimetres. So using that formula is actually not that hard. Right, beats. Okay, when you have two tones or harmonics and slightly different frequencies, so let's go back to that. Then what you can actually do is you can actually hear a beat. Right, so beats are heard when two slightly mismatched tuning forks sound together. So you can have a go at doing that, but I think if we use the online tone generator I've got here to show you, I think that might give you an idea. So what I've done is set this first tone up to be 256, and I'll now play this one as well, 256. Now you can't really tell any difference between that. If I change the tone, the frequency of that slightly, hear that beat? So that's what we're talking about. If I go back to 256, you can only hear one sound. If I go slightly below, you can actually hear the beat there. Alright, so that's what we're talking about with beats. So when you're playing tunes and you have a sound very, very close to that, that's how you actually set up a beat on a musical instrument. I'll just stop that. In this video, hopefully you've understood what the term resonance relates to, so you understand what that is. We've looked at a couple of examples where resonance is actually a good thing, and a couple of examples where resonance can be quite a destructive influence as well. Hopefully you understand that what the node and antinode are for a standing wave. You should hopefully understand what the harmonics are for a particular standing wave. So you have your first, second, third harmonics, and then we just talked about beats and how they operate. So hopefully you've understood all of that. If not, I'd suggest that you have a look at the other videos that Paul Anderson has actually done that go into those things in a little bit more detail.